Hello, my name is Robert, and I'm a senior Flutter developer at Lincoln, and today we'll be talking about using Dart FFI for compute-heavy tasks. So yesterday we had some talks about FFI already, but mostly focusing on integrating with existing libraries. Today we will focus a bit more on the compute and performance aspects of using FFI. So let's start with defining what FFI is, so we are all on the same page. So FFI stands for Foreign Function Interface, and it's a way for Dart or other languages to communicate with other libraries written natively. So in the case of Dart, you can communicate from Dart with a native library. The only requirement is that this library exposes a C an API in a C calling convention. And also Dart FFI allows us to manage native memory, so we can allocate, free, and access natively allocated memory. So there are few use cases for FFI. The one covered yesterday was using it to integrate. Sorry, okay, can you hear me better now? Okay, perfect. So yesterday we covered the integrating with native libraries. So for example, SQLite 3 is a native library which we can link with FFI. The second use case is integrating with the platform APIs, but it does work fine for iOS. However, on Android, it's important that the Android NDK APIs are fairly limited in comparison to the Java Kotlin APIs. I think something is wrong with the sound. Can you switch this mic? Okay, so this mic sounds a lot better. Okay, so second use case is integrating with the platform APIs, so calling the Android NDK or iOS APIs. However, for iOS it does work pretty well because everything is available from Objective-C, which we can expose in a C calling convention and call via FFI. However, for Android, the Android NDK SDK API is fairly limited in some cases. And the third use case that we'll be focusing on is implementing high performance algorithms. So let's first discuss what other options we have than FFI, because FFI is not a silver bullet, and there are disadvantages of this approach. And the first obvious option is using just multiple threads within Dart. So staying in the Dart ecosystem, but using multiple threads to compute our task in parallel. So the main problem with using threads in Dart is the implementation of threads in Dart. So threads are exposed as isolates, which, as the name suggests, are isolated. So they do not share any memory, which basically means that whenever we want to do some computation on a larger amount of data, we need to copy this data from the main isolate to the worker isolate, which obviously reduces the performance. There is technically a class that sounds like it solves this issue. It's called transferable type data, and it allows us to move a type data between isolates in constant time. However, while moving this data is fast, creating the transferable type data does take time proportional to the size of the data. So we first need to create this type data, and second problem is that transferable type data can be used only once. So we can use it only once to move between two isolates, and to copy the result back in many cases will require creating a new transferable type data object, and again we'll lose some time and some performance because of that. The third issue with isolates is the asynchronous communication. However, in most cases it's not really critical since we are doing some heavy computation. So in most cases it can be asynchronous and it doesn't affect our application. However, it is something worth taking into account. So basically, isolates can be useful. However, they are significantly less useful for computation that require a large amount of input or output data, and that this data cannot be loaded directly into the worker isolate. So of course it's fine if we want to load some data from a file into the worker isolate and then output just the result, which will probably be smaller in many cases. So the second option is platform channels. So for platform channels, we can communicate with the native in the Android and iOS sense, Kotlin, Java, Swift implementation. And of course, Kotlin and Java are faster than Dart, not by much, but still faster, and also give us some more advanced tooling for performance application, because obviously those ecosystems are more mature than Flutter and Dart currently is. However, we have exactly the same problems in many cases as with isolates. It's literally the same image, just with different labels. Again, we do not have any shared memory between Dart side and the platform side, so it also requires copying the data to the platform side and then back. And also we have additional problems because we are switching languages this time, so obviously we'll have slightly different takes. And also because we have platform-specific languages, so Kotlin and Java on Android side and Swift or Objective-C on iOS side, we'll need to create two implementations to support those two platforms. And obviously, if we want to support Windows, Linux, etc., there will be even more implementation possibly. Also, platform languages are usually not as fast as they could be. So in comparison to say, they are quite slow. And same as with isolates, we have only asynchronous communication for the platform channels, at least for now. Okay, so FFI. As I said, FFI is obviously not a silver bullet, so it also has some advantages, but also some drawbacks. So for FFI, we do get access to low-level high performance languages such as C, but of course it comes at a cost. The C isn't fast for no reason, and the reason in many cases is there is a lot less safety features, and the safety net is greatly reduced. There are less safety features, and we can much more easily shoot ourselves in a foot. And obviously, since we are Flutter, Dart developers, we may have some experience with C. However, it will be limited in comparison to Dart or even Java, Kotlin, etc. in many cases. So we are also trading performance for lower familiarity with the languages. On the plus side, with C, we do get access to many optimization techniques, such as SIMD, which we'll be using later. Also, we can often make our code portable between Android and iOS. However, while the differences between platforms are mostly irrelevant, we do get another differences, because with some features will only be available on specific architectures. For example, we'll be using Neon with SIMD, which is ARM specific technology. So we may be limited in some other ways. Obviously, we do need to manage our memory manually in most cases. However, there are some tools that help with that, and we are getting more complex build process because we are introducing additional compiler into the mix, and we need to link all of this together. Okay, so how much performance we can actually gain? So Debian is performing benchmarks on different languages. I know those graphs are quite hard to read. They're in two parts, and there is some overlap between them. But Dart is right over here, and it's around 5 times slower than the fastest implementation. And fastest implementation is obviously C. Java and Swift are over here. They're slightly faster than Dart, but not by that much. And C is right here. It's the benchmark. Sure, I will try to speak louder. So C is the benchmark against which we are comparing other languages. So Dart isn't that fast, but it's still a lot faster than all of those interpreted languages over on the right. Okay, so how to use Dart FFI? We'll need two packages. First of them is from the standard Dart library. It's the Dart FFI, and Dart FFI provides us with the native types that we'll use to define our C library on the Dart side. It allows us to load our dynamic library because we'll be dynamically linking our library, so we will have to load it during runtime. We have functions for looking up the functions and symbols in our dynamic library. And last but not least, we have the native finalizer, which is a pretty nice convenience feature. And native finalizer allows us to attach a callback to a Dart object that will be called when this object is garbage collected. So it allows us for sort of automatic memory management, because in most cases, if we allocate some native resource, it will have some corresponding object on the Dart side, and we can attach a callback to this Dart object, which will free those resources on the native side. However, there are some drawbacks here, some caveats. So first problem is that while native finalizer is guaranteed to be called before the isolates shuts down, it will be called only when the garbage collector runs. So if we are allocating significant amount of memory or taking up some other significant amount of resources on the native side, we may still want to manually dispose this object, not depending on the native finalizer, to free those resources as fast as possible. The second problem is that garbage collector in Dart doesn't take into account the natively allocated resources in deciding whether to run or not and when to run. So it is possible that we are taking up significant amount of native resources, but the garbage collector doesn't run because it basically doesn't know about those resources. Okay, the second package is the FFI package from pub this time, and it provides us with methods for allocating and freeing the native memory, so malloc, calloc, free, etc., and also some convenience methods for converting between Dart strings and native strings, because in the native world, string is just an array of characters with a terminator, and also strings are allocated on heap. So we need to move strings from Dart heap to the native heap manually, and also we'll need to free those strings as well. Okay, so we can switch to the code for a moment, and here we have a very simple example of Dart FFI in now just Dart. It's based on the official samples in some part. So we have very simple library with a struct for a coordinate object. We have some method that takes structs. We have a method that reverses a string, and we have a method that frees bitmap. We can free the bitmap using just a free, but I wanted to have some indication of when this freeing is happening, so this function provides us with that. And on the Dart side, so for now we'll skip the part about compiling all of this. Let's just assume we have the compiled library. So on the Dart side, how do we integrate with this? First of all, we need to find our library, because depending on the platform, the location of the library will be slightly different. The name of the library will be slightly different. So we need to provide this path depending on the platform. Second up, we need to open our dynamic library, so load all those symbols, and then using this dynamic library, we'll be resolving those symbols to a functions in Dart that we can actually call. Next up, we'll start with the reverse function that just reverses a string. So we need two type defs, or we don't necessarily need to create type defs, but we need to provide types for both the native implementation that uses those types from from FFI package. So, for example, int32, right? There are multiple representations of int in C, and we need to provide the Flutter type. Here for the string part, it's the same. We're just returning a pointer, but for the int argument, we are using standard Dart int, and it will be automatically converted into int32. And then we can look up our function, providing those two types and the name of the function in our native library. Structs are a bit simpler. We just define a class that extends struct, and we need to define our fields as external, which means that they're using external memory for actual implementation, and we need to define the native types of those fields. Also, important caveat here: we cannot just use standard Dart constructor to create a struct that is available to the native side. So we need to use this struct create method that will create our struct, and then we can assign those values. Alternatively, we also can have a method that's a function on the native side that allocates the struct and returns it to the Dart side. And we have the create struct method, create coordinate function here that does exactly that. We can pass structs directly to the function, and they will be copied to the native side and passed directly. So working with structs is pretty simple. And we have a function here that calculates a distance between two coordinates using the Pythagorean theorem. And last but not least, we have example of using the native finalizer. So we need to define our class and implement finalizable interface in it, and then we need to define the finalizer. So finalizer is a global single object for this for a specific callback. So finalizer only takes the callback. In this case, we are using the free bitmap function from the native side. We also could use the free, I believe it's called native free. So we could use also a free method provided to us by the Dart FFI by the FFI package from tab, because this function just needs to take a voider to pointer to a void. Let's go back to the free bitmap, our implementation, and then in the class constructor we'll attach this object to the native finalizer and provide the pointer that will be passed to the free bitmap function when this native bitmap class is deallocated. We have also here a function to manually dispose this function. So we detach the finalizer, so it's not called anymore. So we don't free this memory twice, and we are freeing manually this data pointer. Okay, so we can run now our example, and we'll go through the main quickly. Okay. One more important thing here in the actually using those functions. So as you remember, reverse function doesn't take Dart strings; it takes pointers to a native string. So we need to convert our Dart string backwards into a native string, into a pointer to a char, and then we can pass this to the function. And then once we get the result, we need to convert back to the Dart side. So there is a bit of work to work with strings and pass them correctly. And obviously, since we have allocated those strings on a native heap, we need to free them after they're no longer needed. On the coordinate side, we can just create coordinate using the constructor we've defined, or we can create one using the function on the native side, and then we can pass them to the function. There is not much here. And lastly, the native bitmap. So here, currently everything works as we would expect. So we created the bitmap. Bitmap became inaccessible once we've left this this block, and then our bitmap has been freed. This is the log from the native library, and then the program finished. So it now all looks good, but it's only because here we are stressing the heap and triggering the garbage collector to run. If we remove this this part and try to run it again, we'll see that the program first finished. We got to the last line of our main function, and then the bitmap got freed only when the isolate was shut down. So we cannot always depend on native finalizer releasing our resources as quick as we would expect it. Okay, going back to the presentation. Next up, how can we use the Flutter Dart FFI in Flutter, because that's the topic of the talk. So we can use FFI plugin for it. So as usual, we would like to extract our dependency to a specific plugin, and we can create one with Flutter create method by passing the plugin FFI template and passing the platforms that we want to support. In this case, it will be Android and iOS, and obviously we need to pass the name. And Flutter will generate a few different parts for us. First up, it will set up the build process of our native library. So on the Android side, it will generate a piece of CMake that will compile our native code and give us a Gradle configuration that will include this CMake into our Android build. On the iOS side, we'll get a Cocoapath configuration that compiles our native library, same as it would compile a Objective-C or Swift code in a standard iOS plugin. And it will generate for us the library loading setup, so all of this resolving of the path to the library and the opening of the dynamic library, and FFI gen configuration. FFI gen is a library that generates bindings for us, so all of this lookup functions based on native C headers. Okay, let's now go to the Flutter example. Actually, let's create the Flutter plugin, and let's take quickly look at what gets generated. Okay, we don't necessarily need to wait for the packages to resolve. So starting with the CMake, it's just part of CMake that builds our library. On the Android side, we have the build Gradle, which includes this CMake as the external native build into our Gradle build workflow. Similarly, on the iOS side, we have podspec that defines our iOS plugin, and here in classes we have one weird part. Because PubSpec doesn't support relative paths, and we would like to have a single implementation for both iOS and Android, we are including a C file inside the iOS specific part that just includes our library relatively from our common implementation in the SRC. So we are using the same files for both Android and iOS implementation. Here we have some example methods that are summing to numbers. And the FFI gen configuration, here we have defined the definition of our FFI generation. So it will use the FFI plugin header file to generate the bindings, and we have those bindings right here. And as you can see, we have it's resolving the symbols and then resolving them as functions and exposing them to us as standard Dart functions that we can Dart methods that we can call. And here we have the opening of the library, so we find the right file and load this library into the FFI plugin bindings class. Okay, so going back to the presentation, real world performance. So we will be using two examples. Both are from my side project, which is a pixel art graphics editor app. So there are quite a few graphics algorithms that are quite compute heavy and need to be pixel perfect. And specifically, we will be looking at alpha premultiplication and flat fill. So what's alpha premultiplication? Since you may not be knowledgeable with the graphic specifics. Basically, there are two ways of storing bitmaps. We can either have pre-multiplied alpha, which means that R, G, and B channels are multiplied by the alpha opacity value, and this has certain advantage in terms of performance of them then composing those bitmaps together. And I need to do this because Flutter requires pre-multiplied bitmap when converting to the UI image object that can be used by Flutter. Here's the algorithm for the simple algorithm for the alpha premultiplication. We're basically going over all pixels, multiplying the RGB values by alpha, and then dividing them by 255 and writing them back. Super simple. Here is the optimized version that doesn't use any divisions, only multiplications, additions, and bit shifting. So in theory, at least it should be faster, but in practice, it's not always faster. So on iOS, we are actually losing some performance by using this optimized version. However, on the Android side, it does provide significant performance improvement. So the takeaway is you have to measure things because the results aren't always what you would expect. And we have comparison with FFI implementation. So by just switching to the FFI, still the unoptimized version of the algorithm, we are gaining 45% better performance, or reducing the time by 45% on Android, on iOS, and 63% on iOS. This is compared to the original not optimized version here. And with optimized algorithm, we are gaining 52% on iOS, and this is the actual comparison between the fastest possible implementation in Dart, because it's the unoptimized one, and the fastest possible for now with FFI. So we've reduced the time by half, so it's not 5 times, but it's still not bad. And on Android, the gain is slightly larger, although we are comparing against the slower version of the Dart implementation. Flat fill. Flat fill, as you may know, it's the bucket tool in the MS Paint. On the left, we have some animation of how it works. On the right is the actual pattern, actual bitmap that we will be filling in. So it's like this squiggly line. So it's pretty long in execution, since we are starting in the left top corner. And results on iOS, by just switching to C, it's exactly the same algorithm. We are reducing the time by 57%, and on Android the gain is slightly smaller at 40%, but it's still quite significant without any additional optimization other than switching to a different language. So how fast can we actually make it using all the optimization techniques that are available to us in C? So first, obviously, we can use multi-threading, but we can also do it in Dart. And we have in Dart 2 implementation. One is using the transferable type data, and actually we are losing performance using it. So the overhead of copying the data between isolates is higher than the performance gain we are gaining by using multiple threads. By the way, we are using 4 threads in all of the examples. And we have the multi-threading with using native memory, because it's on the native side, it can be accessed by all isolates. So we can use FFI tools to efficiently move data between isolates, because we can resolve this pointer in all isolates. So with this implementation, we are reducing time by additional by 39% on iOS and 52% on Android. And now we are comparing against the fastest possible version of the Dart. So the unoptimized version on iOS and optimized on Android. And of course, we have the C multi-threaded implementation, which reduces the time by 80% on iOS. So finally, we got to this 5 times performance boost we wanted, and 73, so a bit less on Android. So next, we can optimize it further using SIMD. SIMD stands for Single Instruction Multiple Data, and basically modern processors are able to compute multiple separate parts of data in parallel on a single thread, as long as we are doing exactly the same instruction. So it's a perfect use case for alpha premultiplication. It's a perfect use case for SIMD, because we can process the red channel of 8 pixels in parallel, because we need to multiply all of them by their appropriate alpha and then divide it by 255. So it's really simple to optimize with SIMD. Yeah, so with SIMD, technically there are some SIMD features in Dart. However, they are both fairly limited at this point, and also there are issues that they have some performance issues themselves. So I haven't tried it, but it seems that SIMD isn't feasible for now in pure Dart. So with SIMD, on a single thread, we get around 10 times performance boost on iOS, and 83%, so a little over five times on Android. And with multi-threading and SIMD, because SIMD is is an optimization per thread, we can reduce the time by 95% on iOS, so over 20 times faster, and 80% on Android. So we actually lost some performance by introducing multi-threading. So basically, we have made the computation so fast using SIMD that the overhead that additional threads introduce make it lose performance. We could technically use some thread pool or some other techniques to make multi-threading more efficient, but it's harder to compare, and we need to then think about multiple thread pools working in the same app possibly. Okay, and last but not least, you may think that GPU is the answer, and I've tried implementation on a GPU using Metal on iOS. However, the overhead of copying the memory from the CPU to the GPU in case of this computation isn't worth it, because our computation per pixel is super simple and super fast. So we are losing more by doing the copy and by actually starting the computation on the GPU. There are some tildes around this number because I've switched the methodology of measurement slightly, so we shouldn't directly compare those numbers together, although they should be pretty close. Like, we shouldn't technically compare them, but we can, at least in terms of like order of magnitude. So yeah, the Metal implementation was similar to the optimized FFI C implementation. And since it's Metal, it's iOS specific, I didn't run it on Android. Okay, so in the end, we were able to optimize our alpha premultiplication by 20 times on iOS, and 13 times compared to the fastest implementation in Dart, so the multi-threaded implementation in Dart on iOS. Okay, so I think we have a bit of time for questions. You can also follow me on Twitter. All the examples are available on GitHub except for the Metal one. And if you're interested, there is also a link to the app I've mentioned. Sure. There is a microphone somewhere, I think.
Hi, I missed the first couple minutes of your talk, so my apologies if you covered this. But what sort of operations do you think are most likely to benefit from dipping into to C or other more performant code bases? So when we're looking at different operations we're trying to implement, what ones should stand out as areas that we should consider FFI for?
Sure. So basically, it will be anything compute heavy. So obviously, we don't want to write. Most of our 95% of our applications should stay in Dart. But if we're dealing with computer graphics, as in this case, with some machine learning on more lower level, unless we're of course using some framework for computation that will use FFI under the hood probably. Yeah. So also, I think you probably shouldn't optimize things until you have to. So once you notice that something is too slow currently, then you should explore the alternative options and actually make it faster. But measure first, and then try to optimize, because also often bottlenecks aren't in the places you would expect them to be.
Thank you.
Okay, thank you very much.